Did you have a good weekend? Yeah? A little bit cold though, right?
Mm.
Okay, well, here we are, one more week into geomechanics. I hope that you're having fun so far. I hear that yes, you're having fun, so I'm glad for that. This week's gonna be more fun. Why? Because you're gonna go to the laboratory and crash rocks on your own. So remember, Wednesday and Thursday at the time of your section, you should go to the lab. Jeffrey's going to be there, and he's going to show you how to measure Young modules and how to also measure unconfined compressive strength. Something we didn't talk about yet, but we'll talk about that, I believe, next week. Yes?
What should we print out and bring from the lab manual?
Nothing.
Nothing?
Nothing, because we have a copy of the lab manual in the lab. So there, you're gonna get, you're gonna see all the material, and Jeffrey also is gonna give you some handouts that are gonna help you summarize your results. So bring nothing except your long pants and your closed-toe shoes. Okay? I think it's gonna be cold anyway, so very likely you're gonna have long pants and closed-toe shoes. But remember, as it gets warmer throughout the semester, you should bring your long pants. Okay, so let me move over here, and it's been 3 weeks already, and we have talked about stresses, vertical stresses, pore pressure, horizontal stresses, but we said that we didn't know how to measure those, and we didn't know how to calculate those. Well, today we're going to see the first method that's going to allow us to compute horizontal stress. I think it is an equation you already know, but probably you don't know where it comes from, and that's what we're going to see today. We have seen in previous classes how to determine Young modulus and Poisson ratio. Let me look for my sample. See where that is. I'm sure I put it in my pocket. Oh, here it is. Okay. So here's the sample. We know that if we apply stress in one direction, it's going to shorten in that direction, but also it's going to expand in the other direction, right? We call that the Poisson effect. Most rocks, they exhibit this behavior, and they have a Poisson ratio, which is between 0 and 0.5. Okay, so we're going to see the effect of the Poisson ratio today. So if I were to take this same experiment, like the one I have over here, and I want to write what is going to be the strain L09-1 as a function of this action sigma 33, what is going to be that value? So when you think about that, I'm going to complete this. I want to calculate epsilon 1, epsilon 22, and epsilon 33 for in a given applied sigma 33. I want to complete some spaces over here in a bit. Just going to put plus, plus, but basically what I want here is an equation that tells me what is epsilon 33 as a function of sigma 33. So this is the easiest one. What should I put in here?
Young's modulus.
For this equation, the third one. You see that equation?
1 over E.
It's the same, so it's going to be 1 over E. And I like to have similar equations over here, also that are going to tell me what is epsilon 11 and epsilon 22 as a function of sigma 33. So what is going to be this value over here? So notice that epsilon 11 is equal to the Poisson ratio times negative epsilon 33, right? But we know what is epsilon 33, which is this thing. So epsilon 22 then is going to be negative Poisson ratio times epsilon 33. And epsilon 33 is this, so this is going to be minus Poisson ratio divided Young modulus. And epsilon 1 is going to be the same. Is it clear why? So I'm going to write it here. Remember that epsilon 11 from this equation right here is equal to negative Poisson ratio times epsilon 33. But I know what is epsilon 33 because I have it right here, so it's just, this one is epsilon 33. Let me ask you something else. Is this stress sigma 33 going to produce any shear stress? What do you think? Yes, no? So I look at this solid over here, it doesn't look it's getting distorted with the shear stress, with the shear strain. So this normal stress sigma 33 is not going to produce any shear strain. So I could complete these equations by writing epsilon 12, epsilon 13, epsilon 23, all of which are shear strains, and there is no contribution at all of sigma 33. If there is no contribution, then here I should have a 0. So sigma 33 doesn't have any impact on what are these strains. Okay, so now I can do exactly the same, but instead of having here sigma 33, I can apply a sigma 11 coming in this direction. And if I apply a sigma 11, I'm going to get very similar equations to these ones, but they're going to be in different directions. So for example, if I were to apply here the stress sigma 11, that stress sigma 11 would cause a strain in direction 1 proportional to 1 over E. And those would also cause strains in direction 2 proportional to negative Poisson ratio divided 1 over Young modulus, and the same for direction 3. And if I apply now stress in direction 2, normal stress, the direct proportionality is going to be here, and the Poisson ratio effects are going to be over here. This is a negative Poisson ratio divided Young modulus sigma 2, Poisson ratio divided by modulus sigma 2, and over here it also is going to be 0. So I'm not going to write them down, but it's just going to be zeros. Well, just let me write it down just for the sake of completeness, but they're going to be zeros as well. What is going to produce a shear strain? You were pointing out something.
The second, the E22.
Yes.
The first, where you have 1 over E, is it?
This one?
Stress 1, 1. Yeah.
Yes. This
Sigma
one
on the
is
second.
sigma 1. Yeah. Sometimes writing all these indices you may get confused. So these are all sigma 1, all sigma 2, all sigma 3. Yeah. Thank you for that. So normal stresses produce normal strains or linear strains in their own direction, like here, but also in other directions, like this one and this one. But in order to get a shear strain, I need a shear stress. So the only way to produce a shear strain is going to be here by having a shear strain, and this one is going to be proportional to a shear stress, and this is going to be, in this case, sigma 1, 2, and let me take the coefficient. It's going to be 1 over the shear modulus, sigma 1, 2, this is a G, 1 over the shear modulus, sigma 1, 3, and 1 over the shear modulus, sigma 2, 3. And just by convention, we define G and the epsilon so that actually I have to write these equations with the 2 over here. Where I'm not going to show over here, but G is not an independent parameter. G is the shear modulus, and G is equal to the Young modulus divided 1, 2 times 1 plus the Poisson ratio. Okay, so notice that now I have equations for all strains involving all stresses. I can apply stresses not just in one direction, but in any direction, a normal stress or a shear stress, and I will get to know what are those strains. You have a question?
Yeah, I have a question about the signs on, you know, how you picture signs.
Yes.
Can we look at the diagram for a second?
This one?
Yeah. Yes, sir.
Yes.
Okay, so let's just look at like sigma 2, 2, and then you made that one negative, right?
Sigma 2, 2
Yeah.
is positive.
Oh, I mean epsilon 2, 2, the first term, the sigma 1, 1.
Yeah.
Okay.
I made that one negative because if we were to apply a strain in direction 2, like this one, you'll get expansion in direction 3 and expansion also in direction 1. That's why it's negative. I'm assuming that all the time because I put these ones as positive, sigma 1, sigma 2, sigma 3, 3. Those will produce a compression and a contraction, but all those compressions will produce an extension in the other directions. That's why they are negative.
Okay,
Yeah.
I see.
Yes?
So in the equation you wrote for the shear stresses, why do we have 2 times that?
That's by a convention of how we define the shear strain. It's just a convention. Don't worry much about that number 2. But it's a definition of the shear strain and the definition of the shear modulus. Okay, so now that we have all these equations, we can write them a little bit differently. It's the same way if we solve equations or if we solve them in another way, but usually when you use computers, you will do operations between matrices and vectors. And that's why we like matrices and vectors. So I'm going to convert these equations, 6 equations, into a multiplication of a matrix times a vector. So if I proceed to do that, then I'm going to have my strains, epsilon 1, 1, epsilon 2, 2, epsilon 3, 3. Notice how I order those as a vector, but in fact I have now in here all the components of the strain tensor that I need, and this is going to be equal to a matrix that, what is going to be the size of the matrix? If this one is 1 by 6, well, 6 by 1, and this one is also 6 by 1. Sigma 1, 2, sigma 1, 3, sigma 2, 3. I write my 6 very similar to the sigma, so don't be confused by it. 6 by 1. What's going to be the size of the matrix? 6 by 6, right? And what are going to be the components inside the matrix? What is going to be the first component? This is the diagonal component.
1 over E, right?
It's going to be the easiest one. Diagonal component is going to be 1 over E, 1 over E, 1 over E, and if we go to the shear part, it's going to be 1 over G, 1 over G, and 1 over G. And the off-diagonal components are going to be negative Poisson ratio divided by Young modulus, negative Poisson ratio by Young modulus, and here's going to be the same. And we know that these are zeros, so I'm going to go ahead and complete this with zeros. And what about here? What about these elements? What do we put here?
0.
Why 0? So we said before that a shear stress is not going to produce a linear strain. And because of that, all of these are going to be 0. But notice that also this is going to be valid for those ones. What this means is that now a shear, a normal stress is not going to produce a shear strain. So those are going to be 0 as well. And you can see that now we also have a symmetric matrix. Writing these strain tensors and stress tensor as a vector instead of a matrix is something which is called Voigt notation. And it makes simpler to write this operation. If you notice, this is just simply strain equal to, in this case, is a matrix called D,